I'm inserting one record into T1 table.
Okay.
Couple of records. So when I say select start from T1, I see two records. If I delete a record from T1 where T1 equal to column 1 equals to 2, I see only one record. If someone approaches me saying that Ravi, I deleted one record by mistake, is there any way you can get it back? Yes. The deleted record is very recent. So not just recent, it's still in the soft delete bucket. So I
Okay.
quickly set a flag called set show underscore deleted underscore records equal to true. When I do that, there are four flags actually, like invisible columns we are talking about.
Yeah.
Delete
Delete XID. Row ID.
yeah, data slice ID.
Yeah.
So every record, even not only the deleted record, even the non-deleted record also has these extra four columns. So let's figure that out. Let
Sure.
it go out.
Yeah.
This is how you see. One has row ID, create XID, delete XID as 0. That means it's not a deleted record. But
It's
2,
inserted.
yeah, but 2 has a delete XID because someone already did a delete.
Okay.
So it's as simple as insert into T1, select star from T1 where delete XID equal to 38838. The record still exists in the same table.
Okay.
Right? Just as equivalent as selecting and inserting it back. Right. Srinivasa, what we are looking at here is, you're able to hear me?
Yeah, here again.
Let's say I'm creating a table called T2 with column 1 integer, column 2 character of 10, creating a table called T1, sorry. When I insert into T1 values, let me insert a couple of records. When I say select start from T1, I should be able to see those two records. These are the two columns we have created for the table. Along with these two columns, we have row ID, create XID, delete XID, data slice ID. We also have these extra four columns, right?
Yeah.
Very record. This row ID, create XID, delete XID gets stored in our data slices or disks on the top. But the data slice ID gets stored at it is a host. Now what I'm trying to do here is row ID is the memory address, create XID is a transaction that inserted this record, data slice ID is a location in which this record physically exists, delete XID is 0. This is what I'm trying to show here. So similarly, this is a memory address, this is a transaction inserted, there is no transaction deleted this yet, so 0. This went into disk 2. Now what I do is I'll go ahead and delete a record. syntax is I'm deleting from T1 where column 2 equals to Ravi. If I run the same query, same select query, right? This time Ravi is coming up with a delete XID as non-zero. Why this deleted record also I'm able to see because I set this flag. Let me disable this flag. Now if I run it, I see ideally one record, right? Agree so far, Srinivas? I
Yeah.
inserted two records and I deleted one record, so I'm seeing only one record. This is an expected behavior. What is so important in here pressing this point? The importance is the deleted record does not evaporate from the system as it is. As and when you delete, it still stays in the system. Now how can you see the deleted record is? A DBA will do this. Deleted records equal to true. Now once you set this flag and you run the same select query, the deleted record still exists on the system. In fact, it exists at the same location where it was previously located, but with a delete XID non-zero. So if some developer approaches you, you can quickly set this flag and see that okay, these are all the deleted records available. So let me know which one you want me to get it back. Now it's as simple as saying that insert into T1, select star from T1, where I delete XID equal to what we are doing is we are inserting back into T1 table. You might tell me that sorry, this is already in a T1 table, right? No, it was logically associated, but physically it's been removed from T1 table. So when I do insert into T1 table, if you do the same select statement, you see two records with 0, one record with non-zero. Now when you say show underscore deleted underscore records equal to false and run the select statement, you see your original table. You see what I'm saying?
So Ravi, irrespective of setting that show deleted record true or false, irrespective of that, like the data gets, whenever you delete, the data gets stored in the, I mean, it will be stored in the host, but when you set it true, you are able to see those records actually on the table, right?
Right. Anything with delete
Okay.
XID non-zero,
Mhm.
you can only see with this flag. They are by
Okay.
default not visible for normal cell.
Users. Okay.
Now, even though your thing is back, right? The record still exists. The records still exist. I mean, the record as in the deleted record still in the system, right? So how can you reclaim? How can you see? As time moves on, these deleted records will increase, right? And it's a waste of space to keep storing these deleted records. At some point, you have to delete these deleted records also. For example, when you say set show underscore deleted records equal to true, when you are trying to delete from T1 where delete xid equal to, it will throw an error saying that the record is already deleted. You can't delete that again. Right. So how can I push these guys out of system? It's like in a recycle bin, you can right click and say that empty recycle bin, right?
Yeah.
But here, how can I do that? That is where the concept called groom table. When I say T1, so depending upon the backup status of the database called SDB1, it will purge those records, purge those deleted records till that point in time. You see here, Groom processed 2 pages. It looked at data slice ID 1 and data slice ID 2, 2 pages. It purged one record. Now if you run the same select statement, your delete xid non-zero record is gone.
Okay.
Right. So this Groom table is a responsibility of both DBA and developer, but on production systems, it's definitely the responsibility of a DBA to run this on a periodic basis, at least once a week. To just if you don't reclaim this space, what happens is, if you talk about these temporary tables in data warehouse, right, where you use those temporary tables, temp tables in the sense staging tables, what I mean. The staging tables, you regularly insert the data and delete the data, and that kind of DML operations happens pretty high. So you have to clean up that once in a week at least. Right. I'll talk more on this in a Groom table class. There are few more options needs to be checked with Groom table. Okay. Right. So the important point here is when I insert 100 and Srini, it went into a data slice ID 1. When I insert 101 and Ravi, it went into a data slice ID 2 here. Right. Can you tell me when I insert into T1 values 102 Srinivas, to which disk it might go? How many disks first of all I have?
2 disks.
On this emulator I got 2 disks. When I say ngds, it will show me that I have a data slice ID 1, data slice ID 2. These are the logical numbers. They are physically associated with 1004 and 1005. When I do this ng hardware, it will show me what is this 1004 and 1005. This 1006 is a spare disk. In a latest emulator 7.2, they are giving only 2 disks. In an older like 7.1, you have like 4 spare disks at least. Not spare disk, 4 active disks. But they reduced it. So in 7.2 emulator, they are giving you only 2. So out of the 2 disks, these disks have been logically called as a data slices, and you got a number for it. 1 and 2. Got a number as 1 and 2. So when you insert a record, it will go to data slice ID 1, means it is physically located in 1004. When it goes to 2, it physically located in 1005. Alright. Now what I am trying to show you here is, what if I try to insert a record called 102? To which disk, either 1 or 2, it will go? Any thoughts on it? When I inserted this record 1002, where did this go? Where did this new record go?
Based on the partition, like what we selected, I mean in terms of Oracle, but here I think it is
Right. Right.
hash or random.
Right. That's the similar concept here is a distribution. So it can go to any of the disks here, any of the data slices. So if you look at here, this guy went into disk 2, right? But the point I'm trying to make here is, when I insert now 103, now 103 went into disk 2. Now what I do here is, I insert same 103, but this time I change column 2. I can confidently say that here, this 103 now will go to same data slice ID. This 103 will go to same data slice ID. If let's say I'm trying to insert 101, I can confidently say that this 101 will go to disk 2. Why I am saying this confidently? Because when I describe this table called T1, along with the table definition, it will show at the end on what column it gets distributed.
So first column.
Yes. By default, the distribution happens on first column on a hashing algorithm. Right? By
So
default,
Ravi,
go ahead.
default is random or hash?
Default is hash on first column.
Okay. Okay.
Right. However, if I create a table called T2 with column 1 integer, column 2 character of 10, distribute on random, that extra clause I have to specify if I have to get it distributed in a random. When I describe T2 table, we can see at the end saying that it's getting distributed on random or round robin. Now what happens when I insert into T2 values 100, same inserts like T1 I'll do here. So it went into data slice ID 1. Now what happens is if I'm trying to insert same 100 and this time I say Srinivas, I cannot say with confidence that this will again go to disk 1. So look at this time it went into disk 1. In a random, my confidence is 0 in guessing the or in predicting the data slice ID. But however in hash, in certain scenarios, I can predict which disk it will be based upon the previous history. For example, if I insert 101 again here, it will go to disk 2. Doesn't matter what the data you are inserting apart from the column 1, because the distribution key or a partitioning key in Oracle terminology is a column 1 here. As long as you have the same data, it won't sit in the same data slice ID. But in case of a random, it's not possible, right? First of all, let's try to understand what is a distribution, right? What are two types of distributions? Why it is important for me to distribute the data, right? Let's try to answer the third question first. Why do I have to distribute my data, right? If you are familiar with the partitioning, it's a similar concept. Why do I have to partition my data? When my data becomes so huge, and if I try to keep all the data in the same disk, my selects or updates are going to suffer, right? If let's say I have 96 million records, what happens if I store all of them in a single disk, right? All 96 million are here, all 96 million are here, right? So whenever someone is going to read, they have to read all this data, or they have to update all this data. Even unnecessary data also you are going to scan. So instead of that, the concept of partitioning came in such a way that identify a partitioning key and then divide. It's sometimes you see this divide and rule, right? It's so apt here. When I say divide, I might say that I use the disk 1 here, I use disk 2, I use disk 3, I use disk 4, right? So here I keep 24 million, 24 million, 24 million, 24 million. When someone is trying to read all the data, these 4 disks can work simultaneously. So my overall select time will be reduced straight away to 1/4. Whereas if someone needs only data from disk 3, it's unnecessary for me to scan disk 1, disk 2, disk 4. But these number of disks are or how many disks to use is all the things you have to take a call in Oracle. But here the same thing has been named as distributions. But this number of disks are fixed depending upon the model you choose. In the twin pin one rack model, that is twin pin 12S blades or one rack, you have 96 disks. That means you have 96 partitions to use. So instead of 24 million here, if we have disk 1, we have disk 2, disk 3, disk 4, disk 96, 1 million, 1 million, 1 million, 1 million. So look how easy it is. That the best thing here is you don't have to worry about what partition to use, how many partitions to use, right? So, requesting Unix team for the partitions. No, this is all pre-built. Because Netezza analyzed it that in data warehousing, it's quite common to have a partitioning. So this disk can be straight away used as a partitioning disks. So instead of 24 million, I'm storing 1 million. Right, if someone is requesting data from disk 3, it's as simple as reading only 1 million instead of 24 million here, instead of 96 million here. Right? So the first and foremost thing as an Netezza DBA you need to concentrate is make sure data for a table is equally distributed across all data slices. This should be your first and foremost thing to concentrate on performance. Make sure data for a table is equally distributed across all data slices. That should be your first and foremost thing. Right. So to make sure that happen, you have two types of distributions. The first one is hash. The second one is random. If I talk about a random, this definitely guarantees me equal distribution of data. Like we have seen in a previous case here, the first record will go to disk 1, the second record will go to disk 2, the third record will come to disk 1, disk 2, disk 2, disk 1, like that it will repeat the loop. It does not worry about anything else, just blindly goes and inserts. But on a bigger scale, when we start inserting like a million records in single transaction, this guy makes sure that the data is equally distributed. But what did I say here? My first and foremost thing is to make sure data gets equally distributed. Then random will suffice here. I repeat. My first objective is to equally distribute the data. If only equally distribution of data is my criteria, random is good enough. Then why do I have to go for hash? First of all, why there is a concept called hashing distribution, right? So that is the objective you need to understand from the next 15-20 minutes, right? If you understand that logic or if you answer yourself that question that random guarantees me equal distribution of data, then why do I have a hash, right? So to help you explain you that, I'm taking an example here. So before I move on, any questions so far? To help you understand what is that hashing brings onto the table, then round robin, right? You need to answer yourself that question. Round robin or a random makes the data gets distributed equally or near equally at least. Then why do I have to go for hashing? What is that hashing algorithm specialty, right? To help us understand, I am making three assumptions here about hashing algorithm or distribution in this case. In this case, I am taking two tables, table customer, table orders. Table customers distribution is on customer key. Table orders distribution key is on customer key. What I'm assuming here, I created a customer table which is distributed on customer key. Very nice. I'm taking orders which is also distributed on customer key. Both are integer data types. And I'm assuming I have only 5 data slices in our Netezza appliance. These are the three assumptions based upon my data. Now I'm showing you three facts here, three universal truths about hashing algorithm. Hash for two similar inputs is always same. Hash for two different inputs is always different. What do I mean that is? Hashing is an algorithm. Takes input and it generates output. When I pass an output of input of 10 to this hashing algorithm, let's say it generates some output. Even after 100 years, if I pass the same input to this hashing algorithm, I get the same output. But please note that other than 10, you will never get this output for any input. So two important rules. This is nothing that Netezza invented. This is an industry standard, industry hashing standard. Hash for two similar inputs is always same. Hash for two different inputs is always different. Same hash values input always goes to same data slice. Now Netezza is using it to its advantage that, so if I send this guy to disk 4, doesn't matter. Even in future, the same output will goes to disk 4. Now this is what Netezza is using for its advantage. Same hash value output will go on sit in same disk. Now if I assume I have a customer record like this. Customer record started with customer ID 19102000, some data. I'm applying a hashing algorithm. It generated A1, B1, C1 and it went to disk 1, data slice ID 1. Like this went to 2, 3, 4, 5, 3, 1, 4. Okay. Like this, these guys went. Right. Now when I talk about orders, so these customers don't sit idle, right? They do orders. So order ID 1 for this customer 2000. But the point to understand here is order is distributed on customer key. That's my assumption. So this input is sent to hashing. The moment I pass 19102000, it will generate same A1, B1, C1. This is an important point to understand. When I pass here 19102000 to hash, when I pass also here, I'll get the same output. Here A1, B1, C1 went into disk 1. So here also this will go to disk 1. When I say this will go to disk 1, the entire record will go on sit in disk 1 here. Is that point clear? Or do you want me to repeat it? Okay. The point I'm trying to make, just to bring everyone on same page again, I assumed customer is distributed on customer key. Orders, surprisingly, I assumed the distributed on customer key instead of order key. So when I say 19102000, it generated A1, B1, C1, go and sit in disk 1. When the same customer orders 1, 19102000, it will go and sit in same disk here. Nice. Like this, the guys went into disk 2, 4, 5. Right? If I talk about 3003, here this is a primary decider on where to store this entire record. This entire record went into disk 5. Here also this entire record with order ID 5 went into disk 5. If I show you the same thing pictorially, this is how it looks like. This is my customer data. This is my orders. When I talk about 5 disks, so customer ID, the associated orders, customer ID, the associated orders, if any, customer ID, the associated orders, if any, coexist in the same disk. You see the logic we are bringing in here. 2000, 1910 customer details and associated order details coexist in the same disk. Here 3002 and the associated order also exists in the same disk. Why they are existing in the same disk? Because both are distributed on the same column. Now what I am trying to show here is table 1, table 2, table 1 is customer, table 2 is order, distribution. Here what we are saying is join column, distribution key, distribution key. I'm saying that customer is distributed on customer key, orders is distributed on customer key. Right. So when both are distributed on the same column, right? Right. So what happens is the associated customers and orders data coexist in the same disk. So this is only one part of a story. This is only one part of a story from storage point of view, right? But if you are a business user, you don't care how do you store the data. I mean, if you are a business user, you don't care how DBA stores the data, right? All you care is how fast are your dashboards are coming, right? Now, let's bring in that aspect of user interaction now. Now, a business user, critical business user logged in and he generated a dashboard. He is running a dashboard that generates this query. You are selecting customer key and orders detail from customers, orders, where customer key equal to customer key. You are joining both tables, customer and orders, on a same join column. Of course, right? You have to join two tables based upon a same join column. Now, what I'm trying to say here is, I'm trying to say your join key is customer key. And when you run that query, these are the three properties of that query. Join column is customer key. Join column is customer key. Table 1's distribution key is also customer key. Table 2's distribution also customer key. When you have all three matching same, right? On the same data, it's as equivalent as doing join within disk itself. See what is happening here? When the join column is matching table 1's distribution and table 2's distribution, your data coexist. Your data coexists in the same disk. So if something like this happens, we call that kind of a join as a co-located join. The data for join coexists in the same disk. The data for join coexists in the same disk. This will never happen with random distribution because random just blindly inserts the data, right? But when you come to hash join, the good thing here is hash has some kind of memory, right? Past history. Based upon the past history, you can take that into your advantage and make sure you get something called co-located join. Now the advantage of this is it's like eliminating at a partition level, maybe partition pruning, some kind of a concept in Oracle other databases. You
Partition wise joins.
Yeah, that kind of a concept. Right? You can eliminate at a partition level itself, whichever is not meeting. Right. So this and with the flexible architecture of 96 disks, we're just talking about 96 disks. When I go to Striper, I have 240 disks. When I go to Striper, I have 240 disks. Right. That means 240 partitions you have.
Partition.
Right. So you can eliminate the data at 240 different levels at the simultaneous time. Right. But the catch here is you need to have all three equal. Even if you don't understand this, open a sheet and write what is my join column, what is my table 1's distribution key, what is my table 2's distribution key. If all pointing to the same, you get something called co-located join. Right? But how feasible is that? How realistic is that I distribute my orders table on customer key? What if I change? What if someone in a design time made a call that? So I'll keep the same query, right? I don't change the query. As a business user, I don't change the query. But at a storage point, from storage aspect, someone, one of your architects or developers took a call that order needs to be distributed on order ID. Now what happens? There is no guarantee that this table 1's and table 2's data coexist in the same disk. Now, what your optimizer has to do is your optimizer has to redistribute. It keeps the original data as it is, and you see you have 33% of a temp space. It has to redistribute orders on customer key at runtime. Right? It still has to bring in same customer data and customer table and orders table in the same disk. So what it has to do is it will utilize the 33% of a temp space to redistribute the order table on customer key. So this concept is called single redistribution. It decides, right? It decides on the fly. We will see more on this in a explain plan. We can understand like on what scenarios it does redistribution. These scenarios. When one of it is not matching with the join column, customer key or order ID. However, there are some scenarios where your customer is distributed on, let's say, country code. Order is distributed on order ID, but you are trying to join both tables on customer key. Then you have to double redistribute. You have to redistribute customer on customer ID or customer key, orders on customer key. You have no choice, you have to make sure you redistribute based upon the join column. So it's called double redistributions. These are nightmares as per Netezza standard. These are nightmares as per the Netezza standards. So you can observe whether your query is doing single redistribution, double redistribution, or a co-located join through explain plan. As a tuning guy, you don't have much options. See, most of the things it will take care. Right? You don't have a redo logs, you don't have this log, you don't have that log, you don't have to worry about the partitioning, how many partitions to give, right? You are limited by what you buy. You are limited by what appliance you bought, right? But the only place where you can start doing the tuning is these distributions.
So, Ravi, by saying this, eventually we will be ending up with like a single or double redistribution, right? Because on a fact table we'll have like multiple dimension keys. So at max we can, I mean, Netezza suggests like only to go with like one partition key, right? So in case like if you want to like join different dimensions with respect to fact, that point of time like we end up with, because fact, if you are having customer key, and obviously dimension when you join, like it will be based on the the business, not business key, probably the surrogate key that what we have on the dimension. So eventually we end up with single distribution, single redistribution, right?
Right. So that's a very good point. The question here is redistribution of a large tables is a huge thing. When I say large table, like a table with 400 million, 500 million, billion records, you end up with a redistribution of dimension tables. Yeah, that's where you have to choose your distribution key carefully, right? We say that fact is a, star model is at a center, right? Don't worry about dimensions too much. When you join this fact against another fact, that's where you have to be very careful with the distribution keys. And dimensions are small tables, right? Hardly like maybe 100,000,
Yeah.
right? That you don't have to worry about. Redistributing them is not a big deal for Netezza. But when you join orders tables with the sales tables, sales details or sales transaction tables, where both of them are like 300 400 gig and 300 400 gig, that's when you have to be careful. So one of the thing that you have to consider while selecting a distribution key is, first thing is you can't update distribution key. So there is nothing like, in Oracle we can update it, right? We need to enable row, something like row movement.
Pro moment, yeah.
Right. Here you cannot update. Second thing is which column is most frequently used to join other fact tables. You can't do justice for everyone, man. If I say customer and orders, I want to do justice for order. What if sales come in picture and it
Yeah.
got distributed on sale ID? You can't do justice for all of it. You have to see which is best in most of the cases.
Maybe something like a time key or a date key, something like that, right? Because at least most of the times like we hit fact table probably 1 month, 3 months, or 1 year or 2 years. So I mean that's what I think of, but is that the way, or is it something we do differently in
Yes.
data warehousing using Netezza?
Yeah, you will be tempted to use a date because you'll be selecting most of the time maybe 1 month of data. But
Yeah.
it's again a trade-off between putting all that 1 month of a data in 1 or 2 disks
Mhm.
against distributing that 2 years or 1 year's data against all the disks. let's say if I distribute my data based upon, let's say based upon year, right? Let's say past 10 years, disk 1, disk 2, I say here that all my 2016 data, I have it here, 2017, 2018, 2019, 2000. So if I keep all my 2016 data only here in disk 6, again you get something called uneven distribution. You might be distributing overall data equally, but your queries will go and hit only these latest chunks, right, most of the time.
Yeah.
That means you are utilizing only 2 disks. So if you use something like that, what you have called processing skew. Your data is not equally distributed. Your data is not equally distributed to get the best performance. So this is not an ideal distribution key. You can't do this with the date. Because when you have a 240 disks, when you have a 480 disks, when you have 720, right? So if you are not sure on what distribution key to use, go ahead for random. Random is not a bad choice. Random still gives you the best performance. If you want the better
Okay.
performance of all, then co-located join. Like maybe 100 or 200 times improvement than traditional systems. So yeah,
But that is again a narrow path only for specific case
right,
when we use that collocated giants.
right, right. So yeah, this is more of a thought process, right? So you cannot update a distribution key. Am I getting processing skew saying that a query is depending on only 1 or 2 disks rather than entire data set? So should I go for year-wise distribution? Should I go for month-wise distribution, or should I go for right customer ID distribution? So the best practice is not to do this. The best practice is find out a column with most number of distinct values and just distribute it.
Okay, but the I mean in the if you think in the other way around, having like 2015 data in one disk, it's always always my optimizer like always only hit the single disk and it gets the complete data quickly instead of reading like 240 or 720 disk and getting the data out. I mean, I'm just thinking because I'm from an Oracle background, so normally in Oracle we try to keep partition based on the the time key or something like that. The reason behind it is like if you hit a specific partition month or a partition year, you only hit those partitions. In that way you don't need to using it uses partition pruning. That way like you get the data pretty quickly out. But if it is distributed, I mean randomly distributed across like multiple partitions, like I mean it's again time consuming, right? I mean that's what my thought process. But I mean my
No, no, not that way. Why I say not that way is, let's say you have like 10 disks here. The moment your query comes, what Netezza does is Netezza will give you 10 threads.
okay,
Either assign
okay,
to 10 threads saying that oh, first thread you are responsible to read from disk 1. Second thread you are responsible to read from disk 2. So it's like 10 employees you have and you have to execute a project. So all work simultaneously. That's the beauty of these AMPP systems.
okay. Got
Right.
it. I think in Oracle we only go with degree of parallelism 16 or 32. I think I understand like that's a bottleneck basically.
When you say degree of DOP, 4 or 5 or 6, you have got only 6 threads to read entire.
Yeah.
But here each one has its by default thread.
Okay.
Yeah, that brings me to a different good point. Another point that we don't have hints here. There is no way you can influence optimizer. Period. Okay. Now
Nice.
coming back here, Srinivasa, any questions so far from your side?
No, Ravi. No.
Please note that distributions is the most complicated topic in Netezza. There is no hard concept than this. This is hard because this is more of a logical in a sense. See, the more you work with data, the more you understand this. If you don't have close working with data in the past, it might be a little complicated. But if you work with partitions before, this is not that hard. But it takes time to understand it. Right? Now let me go ahead and take one more scenario. Apart from this co-located single double, I have one more scenario here. The join column is nation ID. Customer is distributed on customer key. So this time my table 2 is nations. Nations are distributed on nation ID. But one more line I added here is the cardinality. Number of records in T1 table are like 500,000. Maybe I say this 10 million. I'll go for that number. Number of records in nations is hardly I have 300 nations. Right? So join column is nation ID. The query that user is running is select from customer C nations N where C dot nation ID equal to N dot nation ID and blah blah blah. Sorry. So my join column is nation ID. My customer table is distributed on customer key. My nation table is distributed on nation ID. So obviously at the first instance my decision is single distribution because this is not matching with the join column. So this has to be redistributed on nation ID. But this is where optimizer rethinks saying that wait a minute. We are trying to redistribute a huge table in a small table. I understand the single distribution concept. That means whichever is not matching with a join column has to be redistributed. So in our case, customer is the candidate for redistribution. But optimizer then looks at optimizer, hold on a second. Now optimizer relooks at the cardinality saying that customer has 10 million records, nations has only 300 records, right? If I talk about the same 5 disk scenario, so customer table has here 2 million, 2 million, 2 million, 2 million, right? And when I talk about the nations, 60 records. This is an equal distribution, right? Nations has 300 records. This guy here has 5 twos or 10 million. Now host comes into picture here and says that, buddy, instead of you guys redistributing this entire data for just only small result set, right? Small, again a small data. So let me take all the records of nations. 60, 60, and combine them into one large set. And let me put all these large set in a temp area of each and every disk. So that way, whenever any record in this 2 million needs a nation, it's available here. So instead of you redistributing the big table, host comes into play saying that let me bring in all them into one big set and let me send all the big set to each and every disk. That way I can minimize the data movement. So if something like this happens, this is called sorry. You see what I'm trying to say here?
Yeah.
Srinivas? Instead of big stuff, moving the big stuff, what I'm doing here is I'm just doing the data movement of small data. So if something like this happens, we call this as broadcasting. Instead of redistribution of a huge table, what we do is we broadcast a small table. So in general, when you analyze explain plans, you have to look for these four options. Is co-located join happening, single redistribution, double redistribution, or a broadcasting, right? So broadcasting plays a crucial role in performance. Instead of me redistributing 10 million record across the network between various disks, let me broadcast small table, right? So moving on here. So far we spoke about only single distribution. Maximum you can give 4 columns as a distribution case. But this is called multi-column distribution. If let's say I have a customer table which is distributed on customer ID, customer name. If I need to get a co-located join on orders, it also needs to be redistributed on customer ID, customer name. But the moment you increase number of columns in a distribution, the chances of co-located join will come down. Because what is the chance that orders also gets redistributed on customer ID, customer name? And you need to have the same columns in the join condition. So having the such kind of restrictions like join columns, distribution columns of table 1, table 2, all equal is very minimal. So if you cannot identify a single distribution key, instead of you going for multi-column distribution up to maximum 4 columns, better go for random. Better go for random. Again, random is not a bad choice. Random is not a bad choice at all. So here are the few best practices while choosing distribution keys. Avoid multi-column distribution keys. If no good set of columns are available, use random distribution. Do not distribute on floating point and Boolean data types. When you distribute something on a Boolean data type which has only two distinct values, true or false, you will always go for 2 disks only. However, when you distribute on floating point, you get something called met sort join instead of hash distribution, hashing join. Also, don't distribute on random because it is an easy choice. Always look for an opportunity to use commonly joined column as a distribution key. Use same data types for distribution between joined columns. Finally, time spent on determining the best distribution method is time very well spent. Because this is the area that Netezza left it to users. Because it cannot decide your distributions. It cannot decide your data layout. Right? Kind of data you use. So this is a place where people have to spend time doing the performance tuning. But it's not easy, right? Once something goes to production, it takes a long time to change. Right? You might think that, okay, XYZ is a right distribution column, but You don't know how many places people are using that. So that's where your challenge for tuning comes in.
Experience, like what are the, in a normal, say for example CRM or BRM, what keys normally do you suggest? I mean based on your personal experience, is it most of the times people use random, or because as you said you cannot really justify like what when we use a a specific set of columns or a column, so is it random is suggested, or like, I mean, just an, you know.
So initially when we start with something that we don't know where we are getting up to, so everyone thinks that, okay, we might get huge data for this table and that table. It's okay to start with random. All tables just start with random,
Okay.
right? But there is no data at all. When there is no data, when we are slowly starting up the building up a data, probably like 2 years, 3 years, 5 years down the line, why to pressurize the system with hash right away. But slowly when we move into the future, which models are going to get most of the data, right? So that's when
Okay.
right, that's when uh, you realize that which are the tables that needs to be modified for distributions. Also, if the most of the thing is like which model gets joined with what are the fact tables involved. Fact plays a crucial role. You don't worry about dimensions at all. Fact plays a crucial role,
Okay.
right? Only facts. Out of the facts also, which are the most important ones, which has highest data, you just try to avoid huge tables distributions. That's it.
Okay.
Sometimes when you join with dimension tables, right, so they might go for broadcasting. Most of the time they go for broadcasting, right? Also, if you just have a standalone tables, for example, history tables or transaction tables, you don't worry about giving distribution key at all. Random is best for them because you hardly join them with any other tables.
Okay.
But normal scenarios, fact table plays a crucial role. So which are the other facts this is going to get joined, right? That plays again, you cannot do justice on 100 cases. All right. So I'll stop here. Okay. So I'll go with the data loading and unloading in tomorrow's session. That would be complete 90 degrees concept from here. But this is more logical. Think about it and let me know if any queries tomorrow.
Sure, Ravi.
Yeah. So probably we can meet like an half an hour late from tomorrow. So
Okay.
from 9:30 p.m. That's like 7 a.m. Probably 6:30 is too early for universe every day. I'll
Okay.
communicate,
Sure. No problem.
right?
Yeah.
I'll communicate the time.
Sure, Ravi.
Yeah. Thanks, guys. Thanks, Srinivas. Thanks, Srini.
Thank you. Thank you. Thank you
Thank
so
you.
much.
Have a good day, Ravi.
Yeah.
Bye, Srini.
Bye.